Hello again folks, and welcome to another With a Sharpie video. Today I wanted to talk to you about something that flows from last week's video. Last week I spoke about why it is that power stations throw away so much heat and came onto this concept of heat engines and the fact that when you convert heat energy into what we call work or mechanical energy or electricity, there is a mandatory amount of energy that you must throw away. It's to stay in line with the laws of the universe. Well, this week I wanted to talk to you about another way to convert chemical energy in the form of a fuel into electricity, but it's a way to get around that barrier. They're known as fuel cells. You may have heard the term before. I wanted to briefly touch today on what is a fuel cell, how does it work, and importantly, what benefits does that potentially give us going into the future in terms of the way our energy systems work and how efficiently they can work. So, enjoy. Okay, here we are talking about fuel cells. So what's a fuel cell? Well, I think the best way to understand it is in contrast with something that most people understand a little better, which is a power station. So a power station, I'll represent as a box here, takes in a fuel of some kind, and out of that it can generate some electricity. Okay, I think we mostly understand that. If we take a fuel cell is essentially doing exactly the same thing as a power station. So I'll do FC for fuel cell. It's also taking in a fuel and it's also producing electricity. So I guess the original point that you might come up with is what difference does it make? Well, one of the key differences, and I spoke about this in last week's With a Sharpie video, is that a power station has to produce waste heat and it has to throw that waste heat away. And so basically we end up with a lot of this energy that came from our fuel gets converted into waste heat and is thrown away rather than turned into electricity. And so what that means is that our efficiency, or our thermal efficiency rather, which is the fraction of the energy in the fuel that ends up in electricity, is typically for a power station, depending on its type, could be in the range of anywhere from maybe 25 to say 55%. 55% would be extraordinarily good. So we're throwing away typically at least half and often a lot more than half of the energy in the fuel. And the reason for that is that typical power stations are heat engines. So take a look at last week's video if you want to know why it is that all that waste heat is thrown away. And so because heat engines throw away so much heat, essentially we have to burn more fuel to make the amount of electricity that we want. A fuel cell approaches things differently. A fuel cell does not burn a fuel to make heat and then convert it into electricity. It directly, chemically converts fuel into electricity. We'll describe what that means in a moment. But the effect of that is that often our efficiency can be very high. Depends on the fuel cell, but it can be much higher than a typical heat engine. And so how do they work exactly? Well, essentially what we have in any fuel cell, they work under a principle of they have two electrodes. One of them is called the anode and one of them is called the cathode. You don't have to worry too much about what that means, but essentially what happens is we enable our fuel. So let's say we're converting hydrogen into electricity. We could bring some hydrogen in here. The way we would do it is that we would have some hydrogen, which would be brought down here. And what happens is that this space between the anode and the cathode is made of a material or a fluid called an electrolyte, which enables charges to flow across that space in between them. And what happens is that when we send hydrogen into this anode, hydrogen as a gas is known as H2. It's two hydrogen atoms joined together. And what happens is they actually get broken into individual pieces, which we call H ions or hydrogen ions. And they have a little positive charge. And what happens is that they work their way across to the other side. And what you'll notice here is that we started here with something with no charge, and we've now got some things with some positive charge. But charges don't disappear. So what's happened is we've actually produced some electricity. And so there's a circuit here, a wire that goes between the anode and the cathode with some kind of load in between. So that could be connected to the power grid, for example. And we end up with electrons. which are little negatively charged. And they flow down this way. And what happens is that when they meet up with the cathode, these electrons meet up with those hydrogen ions. But that's not enough. We also need something to actually attract our hydrogen ions to that side. And so what we have over here is we have oxygen, which is O2. It's two oxygen atoms joined together. And then they get broken apart into little individual O atoms, ions we call them. And so we've got all these little oxygen floating along. The hydrogen combines with the oxygen and we end up with H2O, or water. Okay, great. So what does that mean in the end? Well, one of the things you'll notice here is that at no point in this did we generate heat. And so effectively what we've got is we've got two little electrochemical reactions going on. One here at the anode and another one here at the cathode, which will enable us to generate some electrons and force them across this circuit here. We've made electricity from a fuel without having to produce heat. Thereby we can get much higher efficiency. So that's great. Why don't we use these things all the time? The main reason is that fuel cells are expensive. So these anodes and cathodes often have very expensive materials. So they might use catalysts and things like platinum and expensive metals like that. Typically you'd need quite a large number of these individual fuel cell elements. So just one of these together we would call a fuel cell. But you need to put a whole stack of them together to get high voltages. So typically an individual cell has low voltage. So if you want lots of voltage, you have to stack lots of these together in what's called a fuel cell stack. But what benefit do these things give us in the real world? Well, first off, fuel cells can be relatively small. So the benefits are that they can be small and there's no moving parts. And so because there's no moving parts, if you think about something like a car, let's say you want to run a car on using hydrogen as a fuel, instead of having a typical internal combustion engine, which is a heat engine converting fuel to heat and then in that case into motion, we could use a fuel cell instead, converting hydrogen into electricity, and then the car is effectively an electric car. So if you think of something like a Tesla car, which is an electric car, they run on batteries. You could replace the batteries with some hydrogen storage and a fuel cell and generate the electricity as you need it. And because they have no moving parts, they are mechanically very simple. They can last a very, very long time. So that's some of the benefits of fuel cells. There are also potential benefits for fuel cells in the electricity grid. So particularly if you're in a region where getting fuel to your location is easy, but getting electricity there is not, say in a remote location, there's potential for fuel cells in that sort of situation as well. This has been David Kearns. You have a good day.